Hello ib3 students. On next recording, next video lesson, this movie is to all of you standard level and higher level students. As I told you last time, today's lesson will be about fluids. Okay, so mechanics of fluids. On the first part, I'm going to focus on a revision from the middle school. We'll be talking about fluids at rest. It will be about the density, pressure, buoyancy, buoyant force, about Pascal's principle. In the second part, we'll be talking about Bernoulli equation, about Bernoulli effect and Bernoulli equation. Today without examples, because this introduction will be quite long, so in the next recording I'm going to present some examples related with Bernoulli effect and Bernoulli equation. Okay, so please note a topic, fluids. Okay, and as first part we'll be talking about fluids at rest. Okay, so as I told you, the first part will be strongly related with revision from the middle school. We must review some quantities or some forces which didn't occur on standard course of diploma program. Okay, so first of all, density. Okay, I hope it's not difficult. You remember that density is the ratio between mass and volume of the object. Okay, remember that density is a scalar quantity. It's not a vector, it's a scalar. Okay, and standard unit of density is of course kilogram per meters cubed. I hope that you have no questions in the case of density, it's easy. Okay, second quantity we'll be operating is pressure. Okay, so what is the definition of pressure? Pressure is force which acts on the area, so it's F over A. So it's of course easy if force is perpendicular to the surface area, but if it's not, then you have to take only value of the force which acts perpendicularly to the area. Okay, so pressure is of course scalar quantity, it's not a vector. Okay, the standard unit of pressure is of course Pascal, and 1 Pascal is when force of 1 Newton acts on the surface area of 1 squared meter. Okay, and you have to know that the value of atmospheric pressure is around 10 to the power of 5 pascals. Okay, and it's related with existence of the atmosphere. So particles of air are attracted by the Earth gravitational force and then creates a pressure on the surface. So at the sea level, atmospheric pressure is normal atmospheric pressure is exactly 101,300 pascals, or 1013 of hectopascals, which is around 10 to the power of 5 pascals. And of course you have to remember that if you have an object, okay, located in a region where there is a difference in pressure, let's imagine that this is a fridge. Okay, here we have a door, and if let's say pressure inside is 2 times 10 to the power of 5 pascals and outside is 1.5 times 10 to the power of 5 pascals, then pressure difference is half times 10 to the power of 5 pascals directed from this inside of the box towards outside. Okay, so this is very, very important that we have to refer to the absolute pressure if we have pressure difference. Okay, and okay, next is something which is related with hydrostatic pressure. Yeah, okay, so next, hydrostatic pressure. Okay, hydrostatic pressure is pressure at certain height or depth. So let's imagine that you have a kind of container, a cuboid, okay, which is filled by a fluid. Okay, container has a height of h and surface area of a. And of course, pressure, which acts at the bottom part of the container, is force divided by area, and force is gravitational force acting on this fluid inside. Okay, mass of the fluid can be expressed by a volume and density, and volume divided by surface area in the case of cuboid is a height. So finally, hydrostatic pressure, I'm going to use index of h, okay, is related with density of fluid, strength of gravitational field, and height of the, let's name it, a column of fluid. If you are deeper under the water, then hydrostatic pressure, of course, is bigger, and it's very, very important, because if you want to find a total pressure, yes, you have to take atmospheric pressure, which is on the surface of, let's say, water, plus this hydrostatic pressure, which is related with depth. Okay, so let's do a simple example. Let's imagine, I hope that you've copied this. If not, please stop video and turn it back when you'll be ready. Okay, so let's imagine that you have a pipe of shape of U letter. Okay. What happens if it's filled by two liquids? Let's imagine that this is something like this. Okay, the blue liquid occupies only this part, and red liquid occupies this part. Which liquid has a smaller density? Of course, the blue one is floating on the surface of red one. It has a smaller density. And let's imagine that you want to check, let's say, the difference in level between blue and red. Let's name it, let's say, X. Okay, and let's imagine that blue liquid has this column has a height of h. How to solve this problem? If the pipe is open, then atmospheric pressure is experienced by two liquids. Okay, but at this depth, a total pressure must be the same. So total pressure on left part must be the same as total pressure on right part. So we can write P left is equal to P right. What is P left? P left is the sum of atmospheric and hydrostatic related with this part of the liquid. So this is atmospheric plus density of red, G times X. The right hand, we have the same, atmospheric plus hydrostatic, which is related with density of blue, times G times H. Of course, we can cross PA, we can cross G, and we have simple relation that density of one liquid times height of the column of this liquid must be the same as density of other liquid times height of the column of this other liquid. Of course, these heights x and h should be measured from the same level. Okay, so this is one of the application of using hydrostatic pressure. Okay, next part of the revision. Okay, Archimedes' law and buoyancy. Okay, so shortly, if an object is immersed in the fluid, okay, it displaces a fluid, and a new force, a buoyant force or upthrust force, let's use buoyant force, starts to act on the object. This buoyant force acts opposite to the gravitational force, and this buoyant force is related with density of the fluid, okay? Because due to the Archimedes law, the value of buoyant force is the same as weight of displaced fluid, which can be written as density of fluid times g times volume of the object, but remember this is volume of immersed part of the object, so if object is immersed not at all, you have to take only this part of the object which is immersed in the fluid. If you want to see more details about this, I've recorded a video for middle school students. You can find it. The name of this the video is buoyancy or buoyant force. I explain in that video this Archimedes law and buoyant force with details, like for middle school students. So this is something we did in middle school. Okay. Remember that when object is floating on the surface, only part of the object is immersed and buoyant force acts only on this part, so you have to take volume of this immersed part of the object, not volume of whole object. Okay? And last part of our revision, the Pascal's law. Okay, Pascal's law, principle, Pascal's law, Pascal's principle. Okay, Pascal's principle is about, let's say, distribution of pressure. Let's imagine that you have something like connecting pipes, connecting containers, okay, and let's imagine that you have two pistons, one here of area A1 and one here of area of A2. What happens if A1 experiences a force? Let's name this force F1. Due to the Pascal's principle, this extra pressure related with existence of force F1, so this extra pressure created by force F1 is distributed uniformly in whole volume of the fluid. So this pressure P1, which is equal F1 over A1, is everywhere the same, which means that in other side the pressure below the piston must be the same. Let's name this P2. Of course, pressure is force which acts on the area, so if area A2 is bigger than area A1, then force which pushes piston up, F2, must be bigger than force F1, because, again, due to the Pascal's principle, P1 is equal to P2. So finally, in this simple system, we have equation force 1 over A1 is equal to force 2 over A2, which can be written in the form of F1 over F2 is exactly the same as A1 over A2. So this simple device, which looks like a typical hydraulic lift, is something like a force multiplier. It can increase the value of force by simple pressure distribution. Okay, and this is known as a Pascal's principle. Okay, and there is one more very important phenomenon which is related with fluids at rest. It's not revision because we didn't do this at middle school, but it's simple. This is something which is known as a hydrostatic equilibrium. Hydrostatic equilibrium. Okay, so let's imagine that you have a fluid. So here you have a fluid. Okay, let's focus on one part, a certain volume of the fluid. If this fluid part of the fluid, this volume of the fluid is addressed, it means that all forces acting on this part must be balanced. So if this fluid has a weight, gravitational force, and experiences a pressure from this side, which creates a downward force on this part of the fluid, and pressure from lower side, which creates an upward force, up, and this will be down, then all forces acting on this part must be balanced. So all forces acting down, gravitational force and force created by pressure from the fluid above, must be equal all forces acting up. So only one force which is rated with pressure of the fluid below this part. So it's visible that force up must be bigger than force down. What does it mean? Then force up, so below the fluid, if F up is bigger than F down, it means that the pressure below related with force up must be bigger than pressure above related with force down, which is coherent with our hydrostatic pressure, because this part of the fluid is located on bigger depth than this part. Okay, so this is something which is known as an hydrostatic equilibrium. Okay, I hope that you've made notes in your notebook. If not, please stop video or move it backward and write all as a revision, because it will be necessary in our second part about fluids in motion or Bernoulli effect. Okay, so stop video, copy this. When you will be ready, turn it back. I'm going to talk about fluids in motion, something new. So point number 2, fluids in motion. Okay, so what is important? In the case of fluids in motion, we have a lot of assumptions. So we'll be talking about fluid which is known as an ideal fluid. Okay, this is something similar to ideal gas, a kind of model. In the case of ideal gas, we have a model of gas. In the case of ideal fluid, we have a model of ideal fluid. So what is an ideal fluid? An ideal fluid is a fluid which is incompressible. Incompressible. Okay, which means that we cannot change the volume of the fluid by external force. It's easy. Okay, the ideal fluid is one which is non-viscous. Okay, what is a viscosity? Is something like a friction of the fluid. So in this model, fluid has no friction. Okay. Next, in the case of the motion of the fluid, we will be talking about something like a steady flow. Okay, this is something opposite to turbulent flow. In the case of steady flow, each point, fluid at one point moves with constant velocity. In the case of turbulent flow, we have, let's say, different velocities when fluid flows through one point in different times. Steady flow means that fluid flows with constant velocity at a certain point all the time. Okay, and the last is we'll be talking about fluid which has no, so doesn't have angular momentum. Angular momentum. Okay, so you know what the angular momentum is. So this is fluid which is not rotating. Okay, so we'll be talking about ideal fluid. So one which is incompressible, which has non-viscous when flow is steady, and fluid which doesn't have an angular momentum. Okay, so this is something like which is known as an ideal fluid. Please copy this. Okay. Let's look. Let's start. We'll be talking about 3 effects today. About something like a continuity equation, about Bernoulli effect, and about Bernoulli equation, and we'll try to derive Bernoulli equation. This is ideal fluid. So next bullet or sub point, continuity equation. Okay, continuity equation links speed of the fluid with cross-sectional area of the, let's say, pipe or region through which fluid flows. Let's imagine something like this. Let's imagine that a fluid flows from this point to this point, okay, through areas. Here we have area A1, and here we have area A2. Okay, and let's imagine that fluid when it crosses area A1 has a velocity of v1. When it crosses area A2, it has a velocity of v2. And of course, let's imagine that fluid in area A1 has a density of d1, and here, where area A2 is located, the density is d2. Of course, fluid flows from this region to this. So from here left, here to the right. Okay, so we have something, you can imagine that we have something like a pipe which changes diameter. Area A1, my graph, is less than area A2, so you will see that speed of the fluid which passes through area A1 is not the same as speed of the fluid which passes area of A2. Okay, so let's take first, what is a mass in unit time, okay, in delta t, of fluid which passes through A1. Okay, so in delta t, okay, the amount of fluid, so m1, which passes through A1, can be written as density times volume. Okay, so let's write density d1 and volume of v1. And what is a volume? Volume is cross-sectional area times distance traveled by fluid in times delta t. Distance when a fluid flows with constant speed through the point, any point in area A1. So distance can be written as the product of speed and this time. Okay? And the same we can write in the case of m2, so mass of the fluid which passes in time delta t through area A2. Okay, so this is density of fluid at area A2 times volume of the fluid, which can be written as cross-section area of this area A2 times velocity of v2 times delta t. Okay? Due to the law of conservation of mass, we can write that m1 is equal to m2, okay, which can be written as density 1 area 1 v1 delta t is equal to density 2 a2 v2 delta t. We can cross delta t, okay, because we've taken the same time this fluid flows. Okay, and of course, so we can say that density of fluid in area A1 is the same as density of fluid in area A2. Why? Because the fluid is incompressible. Okay, so if it's incompressible, then density must be constant. So due to the fact that this is ideal fluid, we can write that density 1 is equal to density 2. So due to this, we can cross d1 with d2, obtaining equation area 1 v1 is equal to area 2 v2, or in other words, A times V is equal to constant. And this statement that the product of area through which fluid flows and velocity of this fluid is constant is known as a continuity equation. So this is continuity equation. So if let's imagine that your fluid flows through the pipe. If area of the pipe or diameter of the pipe increases, then fluid slows down. If area of the pipe decreases, then fluid accelerates and travels with higher speed. Okay? So please copy this continuity equation. When you will be ready, please turn the video back and we'll be talking about the Bernoulli effect. Okay, so I'm changing slide and point pre-last Bernoulli effect. The Bernoulli double L effect. Okay, and let's imagine that fluid travels from this region, thicker, to this region, which is thinner. Okay, remember that the continuity equation says that A times V is equal to constant. Okay, so what happens with fluid? Fluid travels here and enters this very narrow region. Okay, so practically, if we have a steady flow, then fluid here in this region must accelerate. Why? Because the same amount of fluid must pass through the cross-sectional area, or due to the continuity equation, the fluid must accelerate. So practically we have higher speed here, than here. Okay, and Bernoulli effect is about change of the pressure if there is a change of speed. Okay, there must be a pressure difference, okay, with a lower pressure in the narrow section and higher pressure in the wider section. So here, where the lower speed is, there is a higher pressure. And here, if the narrow section is, there is a lower pressure. Okay, so what does it mean? If speed accelerates, or if there is an increase in the speed of the fluid, okay, then there must be decrease in the fluid pressure. And this statement is known as a Bernoulli effect. Okay, so if the greater the speed is, then lower the pressure and vice versa. So write this by words. Okay, the Bernoulli effect is, so maybe here, the greater the speed, okay, then the lower the pressure. Okay, and this statement is known as a Bernoulli effect. Oof. Please copy this. Okay, and the last will be about Bernoulli equation. We will try to derive Bernoulli equation from the law of conservation of the energy. Or maybe let's start. I'm going to give you a Bernoulli equation, then we'll link this with law of conservation of energy. So last point today, the Bernoulli equation. Still we are talking about fluids in motion. Okay? So what is the Bernoulli equation? Bernoulli equation says that the half of density of the fluid times squared speed of fluid particles, okay, plus density of the fluid times gravitational acceleration times height of the fluid, vertical height of the fluid, plus pressure of the fluid must be constant. Oof. So what does it mean? Let's look. We have practically two parts. This part is related with speed of the fluid, so dynamics, so like kinetic energy, and this part is related with height on which a fluid is. When fluid changes height during the motion, then this is important factor. Okay, and this is a fluid pressure, so this is standard pressure which is not related with movement of the fluid. Okay, so if fluid is stationary and is placed on reference level, then it has a constant pressure, just this. Okay, so this equation is known as a Bernoulli equation, and how to link this with a law of conservation of energy. So again, remember, this is something like a dynamic pressure related with motion, and this part is something like a static pressure related with fluid which is stationary. Is it clear? Okay, so let's try to make a law of conservation of energy by using this. Let's look. In the case of first, we have one difference between kinetic energy and this first part of with this dynamic pressure. Except mass, we have density. Okay, so what is the relation between mass and density? Of course, volume of the fluid. Mass is volume of the fluid times density. So let's multiply this left part by volume to obtain volume times density or mass. So we have half of dv squared, half of capital V dv squared plus V. I multiplied this by V. Okay, so V dgh plus pressure times volume. It must be constant because constant multiplied by volume is also a kind of constant. Okay, so now let's look. V times d is a mass, so half of mv squared plus V times d is mass, mgh, and here what is pressure? Pressure is force which acts on the area. Must be constant. And what is force volume over area? Volume over area is a kind of distance. It's measured in meters. So we can write that this is a kind of distance. I'm going to use letter, let's say, x. So on the left part we have half of mv squared plus mgh, and here we have f times x, which is constant. And what is this left part? Is energy, kinetic energy, half of mv squared, plus mgh, gravitational potential energy, plus fx, work done, must be constant. So Bernoulli equation is something like a law of conservation of energy for a fluid. Okay, it consists of two parts. Dynamic part, dynamic pressure related with movement of the fluid, and static part, static pressure related with fluid which doesn't move, or you see that this is something like a hydrostatic pressure plus, let's say, atmospheric pressure. Is that clear? Okay, so again, Bernoulli equation says that half of density times squared speed plus density times strength of gravitational field times height plus pressure, fluid's pressure must be constant. So, in other words, if fluid falls, then height changes, then it must accelerate and vice versa. Okay, we'll be talking about examples in our next meeting. I hope that this lesson was interesting to you. Please make a notes. Next meeting we'll be talking about examples and we'll be calculating something related with Bernoulli equation. Okay, so thank you for watching. Any questions, comments, please write via the Google Classroom. Again, thank you for watching. See you. Bye.